Our next speaker is going to be Ozan Tugluk, who is at Brown University, and he's going to be talking about some of the things that Scott alluded to in his talk, including MGARD, which is, I guess, it's a kind of a smart data compression algorithm. Would be perhaps a good way to describe it, but I think Ozan will tell us more.
Thank you. So let me start by sharing my slides, and I hope you can see my slides.
Yeah, looks good.
Okay, all right. So first of all, I'd like to thank you for the invitation. So it's an honor to be talking to you about my work, and we really hope our experience with ECP CODAR might prove to be useful for you as well. So I'll be talking about MGARD. Thank you for saying it's smart. I don't know if it's smart, but we hope it is efficient at least. So this is joint work with Mark Ainsworth from Brown Division of Applied Mathematics, myself, Ben Whitney, who was a grad student and a postdoc here. Now he works with Scott Klasky's group, and also Scott Klasky, who just spoke. All right. So okay. So here's a brief outline of my talk. So I basically briefly touch on what scientific data compression is. I'll mention what analysis-driven compression, what we mean by it. Of course, I'll be talking about MGARD while I'm doing this. I'll be showing you some examples from computed data sets and some examples, and I'll try to draw some conclusions, hoping which will be helpful for you. Okay, so let me start with this somewhat provocative question. Are you reducing your data? So if you asked me this question in another life, I was a turbulence researcher, I would just tell you I wasn't, because I didn't think I was employing any kind of compression. But actually, most of us probably are reducing or compressing our data without actually realizing it. For example, what Ainsworth likes to call decimation is we save our simulation, say, every 100 steps, every 1,000 steps. So, of course, this would be inverse decimation, but let's go with Ainsworth's terminology and call it decimation. So this is almost all of us employ this, and actually this is ad hoc compression, because while we're going in time, even though we have a sense of preserving the integrity of our simulation, we are actually throwing away data, and nothing changes it. And we don't really have any error bound on what the final effect of this would be on our analysis. So this is just ad hoc compression. One other common method or common way of ad hoc compression is downcasting. So if you compute your if you do your simulation in double precision, then cast your results into single precision. Basically, this is lossy compression. So most people do this as well. I've done this in the past too. So last two, they're not basically ad hoc compression techniques, but maybe you are doing a Cohen love or proper orthogonal decomposition on your data, storing the eigenfunctions and then the corresponding the eigencoefficients. So that would also, if you're truncating it, that would also mean you are reducing your data. Of course, if you are doing KL or POD, you know you are reducing your data. But just this is another technique of reduction and compression, even if you didn't think of it that way. Also, there is this checkpoint restart type reduction, right? For example, you're working in Fourier space, you truncate your Fourier modes. Then when you're restarting your simulation, you just initialize the higher modes with random coefficients, small random coefficients. So this also constitutes a type of reduction. So what we are proposing with MGARD is a fundamentally structured way of compressing your data. Our method is based on, actually the idea stems from the MultiGrid methods that are employed. And we base it on an orthogonal projection. And roughly, so just to give you a main idea, so it works on tensor product grids and cell-based data, currently triangles and tetrahedra. And to tie in with Scott's talk, MGARD is completely integrated in ADIOS. And I think it's called an operator. If I'm wrong, I'm sure Scott will correct me. So you can just call it in a couple of lines when you're doing your I/O. So basically, you can compress your results almost seamlessly, just specify a tolerance, and then you can compress your result. And one distinguishing property of MGARD is we can compress your data whilst preserving your analysis result. So basically, you can specify the accuracy you want in your analysis rather than the pointwise, say, error in your data. you can specify the error you want in the analysis, and then we preserve it in a guaranteed way. So let me just go over some of the highlights of MGARD. So MGARD, as I told you, works on TensorFlow records and cell-based data. On the left, for example, this is a toy example of a Chebyshev grid. Actually, this is Chebyshev in both directions. So MGARD handles these natively. So if you give us a Chebyshev grid, we are happy to compress your data on that grid. There are many lossy compressors around, but they don't really take the underlying physical structure of the grid into account, whereas this is fundamental to the inner workings of MGARD. So one other example is this airflow in fluid flow. Actually, this is a Yokosuka Flow. So if you look at it counterclockwise, so this is your, I hope you can see my pointer. So this is your original mesh. And here you can see our imposed hierarchy on that mesh, which we use for compression. So basically what we do is we take your grid, we impose our own hierarchy on it. So now this becomes something like MultiGrid. So you would have multiple layers, and Scott was touching on it. So you would have multiple layers of progressively coarsening meshes or cells, and then you would basically do an L2 projection on all of these. So you would have a representation on those, and then you can compress that data. I will show you in a minute how to do that. Or you can do partial decompositions, and Scott mentioned this as well. So briefly, our fundamental mathematical structure is built on these 4 papers. In the first one, we've developed this idea on univariate for the univariate case, which is one-dimensional meshes essentially. Then we moved it to multivariate and L-infinity compression. Then we came up with a way to preserve quantities of interest. And then the final in this 4-paper series, we show how to tackle the unstructured case, basically tetrahedra and triangles, obviously. Okay, so basically one example of compressing while preserving the analysis results would be for the Yokosuka Flow. Here you can see the CP, the pressure coefficient. So essentially, we can specify a tolerance on the pressure coefficient and recover it. So we can do this for various parameters. We have a parameter called S. And most of the time, it isn't difficult to determine what optimal S would be. And so basically, you're able to compress your data while preserving what you're interested in. Because when you're doing a fluid flow simulation, you are not interested in the values of the velocities and pressures at each and every grid point when you are doing. Of course, they really, you need them when you're computing to get your results. But in the end, you just want your results to be correct. All right, so I also mentioned MGARD being adaptive in both space and time. So if you do compression in time, it will be adaptive in time. But if you do space compression, it will be adaptive in space. So let me try to illustrate it by showing you a small movie. So on the left, you see an original turbulent channel flow. So this is from John Sofsky's turbulence database. Around 1,000, the friction Reynolds number is around 1,000, 1.6 billion grid points. So on the left, you see the original data. On the right, you see compressed and decompressed data with MGARD to 1% pointwise accuracy. And what we are showing in these blow-ups is where we are actually storing data with MGARD. So anything which is a black dot is where we store information. And if you see a white space, so that means we don't really need to store anything there. We can just reconstruct it from the other coefficient. And of course, if you, I hope you can see this, but if there is more change in the flow, then you will see more dots appearing here, and the weight of the dots just gives you the magnitude of the coefficient we are storing there. So basically, we are adaptive in space and/or time, depending how you compress. So we only keep information where it is needed. Okay, so just let me briefly give you an overview of how MGARD works. So we start with what we call QL of U, which would be your original data as you are starting. So without going into too much detail, what we do is we split your data into 2 parts. And one of these parts, what we call delta, is sent to storage. And the rest is taken and used as an input for the next level or for the next layer of this process. So we start from the initial mesh, recursively coarsening the mesh, generating some structure and separating out some deltas, which are then sent to storage. Then you can use this exact same procedure, which is essentially symmetric. You just go the other way, then you can reconstruct your data. And you don't have to reconstruct all of your data. You can just construct to a, say, given mesh. You can just construct to, say, first 3 coarsest meshes, or you can go all the way to your original mesh. And this is all handled by Mgart. So one fundamental feature of Mgart is error bound. So again, I won't go into too much detail, but essentially what we've shown in our papers is any Sobolev norm or a Sobolev norm for given S, we came up with a family of estimators that basically tie the norm of the given function to the deltas, the things that we are sending to storage to them. So basically, you know how much error you're incurring. If you throw away a coefficient, you exactly have a one-to-one relationship, knowing how much that would affect the final result in terms of your data. So the effect of changing the coefficient on the effect of the original data. That's what I'm trying to say. All right, so this is all fine. So we can do this to compress pointwise. But then, as we were doing compressions, so this probably overused quote, not to mean it's not true. So basically, we all know the purpose of computing is insight, not numbers. So we're not really trying to compute numbers. We're just trying to come up with something, some scientific knowledge or a scientific insight. So, of course, a bit jokingly, we were thinking about, like, can you compress insight? So compressing insight probably would prove difficult. So we said, all right, can you, say, compress lift? Or can you compress drag? Or can you compress while preserving the lift, preserving the drag, if you're interested in fluid flow? So then we said, all right, we need to find a way to compress our data while preserving the quantities of interest with the framework that we have. And then we just investigated this, whether it could be done. And it turns out we can do this very easily after you go all the proofs and everything, of course. So just briefly, what I'm going to be telling you is here Q is a bounded linear functional. And so what you can look at our paper 3 for this. Basically, using the Rees representation theorem, we can compute this epsilon of Q. And then basically, it is just a scaling factor. So it's a scalar if you have a single quantity of interest. And if you have multiple quantities of interest, you would just pick the larger one so that everything is conserved. So basically, you just compute a single number, a single floating point number, a single real number, and that would just come into the error indicator family, and you're set. Basically, everything boils down to computing this epsilon. And with Mgart, if you have a given bounded linear functional, we have a way of computing this epsilon. So basically, let me try to give you some insight on it. The Rees representation theorem says if you have a bounded linear functional in a function space, which we construct, so there is a vector there whose action is exactly the same with your bounded functional. So once you find that vector, if you compute its norm, you basically computed epsilon. And we show how to do this in our paper, and this was, at least in the reference version, this was included. But I think it didn't sit well with all these testings and everything because I was causing probably problems with security using develop and everything. Anyway, to cut it short, this can be done, and we show this. We show how to do this in our paper 3. Anyway, so without further losing myself, let me go to some examples. So using the framework, I just try to outline to you. For example, things that we can do is we can do streamline control. So in this case, this is from S3D simulation. So this is turbulent combustion. This is a quasi-steady case, so it's a bit easier to compress. As you can see from the compression ratio, which is 1700x compression. But what we're trying to show you here is if you set S equals 1 in Mgart without even computing epsilon, you do a pretty good job of preserving your streamline. So you just inject something onto the flow here, some particles, and you trace their path. And so it turns out using S equals to 1 gives you a reasonable approximation of the streamlines in the original case. So if you were to use, say, pointwise compression, you could also achieve something which is close to the original, but then your compression ratio would suffer. So what we're trying to do is compress our scientific results, but get better compression than would be possible using L-infinity or pointwise compression. So this is one example. So we also dabbled with preserving the energy spectrum, say in a turbulent flow. So what this enables us is, if you want to preserve a certain range of wave numbers, say up to 100, up to 10, to a given tolerance, we have a way of doing that as well. So here you can see, as you obviously, as you tighten your tolerance, your energy spectrum approaches the original. But then we provide you with a way of saying, if I said epsilon is 10 to the minus 6, what would be the range of preserved wave numbers? So we came up with the theoretical, here it is actually, we came up with theoretical results that helps us estimate what that would be. And here we're just testing it. So basically, if you want your wave numbers to be, if you want your energy to be preserved, say 10 to the minus 3, in a relative sense, so basically, if you have a tolerance of 10 to the minus 4, you can preserve the first 10 wave numbers to that, and then after that, you will start to see a degradation. An experimental example, so this is from the Gpi experiment. So basically, this is plasma circulating in a tokamak, and they're taking high-speed pictures, and so this, they're confining it with a magnetic field, but it can be, apparently, this field can be interrupted by these spatiotemporal instabilities affectionately known as blobs. So basically, Mgart gives you a way to preserve these blobs, the position of these blobs when you are compressing it. So at S equals -1 or 2, you can effectively preserve these blobs with a compression ratio of 8.5. And so this is just a snapshot, but here we are showing you the first 1,500 blobs. And so what we did was we got the original data, we compressed and decompressed it. Then we ran OpenCV to find these blobs, blob centers. So basically, we are plotting the blob centers, and the blue circles are from the original data, and the red stars are what Mgart is finding. So basically, essentially, we managed to capture most of the structure with a compression ratio of 8.5. Of course, there are some blobs that we are imagining which don't exist in the original data, but they're not that high in number. And overall, so you can basically track the movement of those blobs as well. All right. So one of the final examples. We're showing you what's called the Numeral puncture plot. So these are also on a toroidal geometry. Essentially, so you have a plasma, a magnetohydrodynamic event going on these tokamak or toroidal shape. So you just put an aluminium foil, and then you say, all right, if some particle hits it, I assume it is punctured. So these are like Poincare plots. So on the left, you see the puncture plots from the original data. So this is Mgart, and we determined S equals 1 again would be the way to preserve these puncture plots. And at 10x compression, so this is quite similar to the original. And even with 100x compression, S equals to 1, you start seeing some artifacts, but the islands in the middle and these two crescent-shaped islands are still present. And let me just show you another example. So this is another compressor where you don't get the chance of preserving quantities of interest, but you can preserve the peak signal-to-noise ratio. So again, with this compressor, for example, if you go with 10x, you still get respectable results. So these are very similar to Mgart results with S equals to 1. But then if you go to 100x compression, this is the puncture plot you get. Basically, you just lost whatever you were trying to do. So in this case, using Mgart with 100x compression would be, of course, preferable. So finally, let me just show you this again. So this is from Numeral as well. And these are chaotic field lines on irrational 2-1 surface, basically. So this is the puncture plot I'm talking about. This is the overall geometry. And these are the so-called chaotic field lines. I don't know what they are, but I include them in all my talks because I really like saying chaotic field lines on irrational 2-1 surfaces. So sorry about that. So finally, let me just try to draw some conclusions. So this isn't much of a conclusion, but this is more of an advertisement. But Mgart can compress data while preserving quantities of interest through prescribed accuracy. So you basically specify what you want to preserve in the results of your analysis. So you're not so much interested in what goes in between, but we make sure mathematically guarantee that finally the quantities of interest will be preserved to the given accuracy. So this is more of our impression of working with, or our insight working with data is basically analysis-driven compression is much more relevant than preserving data point-wise, because this is, in a sense, not we're interested in. So we just really need to work on compressing the results, preserving the results of the analysis. Sorry. So as this workshop has to do with visualization and also data flows. So I have to say this as well. So the holy grail would be to provide tighter integration with visualization libraries and I/O libraries, which will enable you to work homomorphically with your data. That means, so you have your compressed data, but the holy grail would be you don't need to decompress it to plot your data or do analysis on it. So this is something also encryption people are working on. So basically, this would be the end results that I think we all agree we should be reaching. So you have your compressed results that then on the disk taking up much less space, but then you can run your analysis directly on them without the need to decompress. So finally, if you want more information, Mgart repo is on GitHub. So Mgart currently is being maintained by Klasky's group, Scott's group in Oak Ridge. And there's some compression benchmarks related to CODAR at strbench GitHub.io. So you can go there and download some of the data sets I've used as well. So thank you. So finally, these are our references. And thanks.
Thank you, Ozan. Very interesting. So we haven't got any open questions on the question and answer at the moment. If anybody has got any, you could perhaps post them now. It's an opportunity. Otherwise, we can just, we've got a couple more minutes. We could just have a brief discussion, I guess. So, I mean, you were talking there, there's a very wide range of compression that you can get, sometimes like thousands of times compression, and sometimes just a couple of times or 10 times. So what's the sort of, how do you know when you're going to be able to compress something really well or not? What's the sort of, for example, when you those features, those blobs that you were trying to follow in the MHD, you couldn't compress those as much as the streamlines. And
yes, so yeah, I mean, basically the answer would be it essentially depends on the data, because the algorithm is always the same. So what happens is, for Mgart at least, if your data is larger, most likely it's going to compress better. But one other thing is, basically, if you have structure in your data, Mgart will just latch onto it, so it will give you better compression. So the streamlines that I'm showing you from S3D, so they are from a quasi-steady simulation. So basically, it's much easier to compress. So probably it was an unsteady simulation, the compression ratio would go down a couple of orders of magnitude. So having worked with these data sets for a while, I can really guess what the compression ratio would be. But the only way to effectively know what your compression ratio is just to compress your data. It's a bit of a tautological answer, but.
Yeah, and mostly you've been working with sort of fluid dynamics in one form or the other. I mean, does this work equally well for other equations, other types of problem?
We worked with, basically we worked with fluid dynamics data, some simulations that Ben has performed on chemical simulations. And basically it works quite well on almost everything apart from particle data, because this is not geared for particle data. So if you have a tensor product structure on your data, chances are it will give you a decent compression.
Yes, Scott, please, please join in.
I mean, I could add, and so Ozan, just, You know, so I think some of you are familiar with like the XGC code. It's a particle and cell code. It's not exactly a fluid code, right? So things are very stochastic. So in fact, one paper that Ozan, I believe you're a co-author, we've been compressing the data that comes from XGC, which is particles. We map that, you know, it's 5-dimensional. We map that over to a distribution function. So it's an, you know, it's a particle distribution function. And then from that 5-dimensional function, you know, I wouldn't really call that fluid-like, right? So what we've been looking at is more of the correlations which go between velocity space, between other spatial vectors. So this is where we were using a lot with the nonlinear aspects of MGARD, but we need MGARD to support very arbitrary unstructured meshes. So I think it really deals, in my opinion, Ozan may disagree, it's the correlations which are in the data. That's what's going to really tell you much more about the compressibility, along with the errors that you're going to allow. But like, to me, like when I give the talk, I mean, to me, what I would say what MGARD is trying to achieve is not errors in the data you're trying to compress, but it's in what Ozan said. It's these quantities of interest. Because who cares, you can compress that raw data. If all the physics is wrong later, if you find that you violate Maxwell's equations later, right? Del B is, you know, large in some areas. That's not good. So you have to preserve this. And I think that's one of the key things. And then can you have a high compression ratio? So we're looking at more of making sure quantities of interest are preserved and making sure that, again, we can maintain that and making the data in this hierarchical. So what Ozan said of like, here's the real thing we want, which is we want to do things so you can, with a smaller amount of data, when you read it back, like climate wants, you can't compress, but they want to be able to read back with less degrees of freedom and do the analysis and have a finite error. And if they take and read back more, then the error can go up. But then make sure the analysis algorithm, as Ozan was saying, scales in the fashion of with the data size. So like, it's not a general compression where you take a terabyte, you compress it to a gigabyte, and now when you read it back in memory, you expand it to a terabyte, and 999 gigs is kind of like, is it really data? It's not real data, right? It's reconstructed to some level of accuracy, but you don't really need it. So we're trying to make sure you can compute off of that reduced data set. So, sorry to jump in.
No, that's great.